All right. Welcome. Move this over here. Okay, things look roughly correct. Okay, so continuing our discussion with scientific notation, right? And I was just looking things over. We're on a good pace. We were not going to have to rush through stuff or anything to finish in time. We're on a good pace. So that means we can sort of take our time, not just overload ourselves with stuff each time we meet, which is good. And as always, if you have any questions or concerns, make sure you communicate those to me, either in the form of meeting with me right after class in Zoom, coming to office hours, whatever it is that you need to do. If like we're kind of getting into the crunch time, and I know people start getting really tired, people are worn out. You have jobs and families and stuff. These classes can start getting away from people. So if you feel like you're starting to struggle a little bit, make sure you make contact with me so we can try to get you set straight again so that you can finish the course successfully, okay? By and large, you're all doing pretty good, but I know we're kind of entering that zone kind of early November, and then we get all these breaks that I don't always think are necessarily helpful. It's kind of nice to get, have a little bit off for Thanksgiving. It's nice to have a little bit off for certain holidays and stuff, but it kind of throws off people's schedules sometimes where they're in a zone of like getting work done, and then all of a sudden they relax, and it's hard to get yourself back in that pattern of working hard. So just stick with it. Most of you are doing a really good job. Keep it up and finish strong so you don't have to take this class again, right? No one wants you to have to take this class again. So we were talking about scientific notation last time, and I was giving an introduction to it. Let's take a look at a few problems just to kind of remind ourselves how this works. Okay. Write the number 1.8 times 10 to the third in standard form. So the basic idea is, since we use a base 10 number system, when you multiply a number by 10, it effectively moves the decimal one direction. When you divide by 10, it moves the decimal the other direction. Right? Well, which direction? Which direction does it move it? I encourage you not to memorize, right? I've even seen books do this where they say, oh, on this case, move the decimal right. On this case, move the decimal left. I find that very antithetical to learning, right? What you want to do is understand, because you're not going to, in a year from now, if I ask you, do you move it left or right, you're not going to remember. Right? But if you understand which direction you're supposed to move that decimal, then it makes sense, and you go, oh yeah, you move it right in this case, right? So when I look at 1.8, if I take the number 1.8 and I multiply by 10 3 times, is the number going to get bigger or smaller? It's going to get bigger, right? It's going to become a bigger number. So if it's going to become a bigger number, which direction am I moving the decimal? Oh, well, I should be moving it to the right, right? So this number, this tells me I should move the decimal 3 places, so that becomes 1, and then 800. So 1800, 1800. Submit that answer. It says, are you sure? Yeah, I'm sure. Right? And so move the decimal place to the right, which is good, but remember, move it to the right. Understand why you move it to the right, and you'll never have to wonder, wait, is this left or right situation? I can't quite tell, right? Let's look at another one. Okay, good. This is what I was hoping. The other type of problem. Now we're multiplying by 10 to the negative 6. So that's the same as dividing by 10, right? Because really we're multiplying by 1 over 10 to the 6th. So we're dividing by 10 6 times. If I take the number 2.1 and I divide it by 10 6 times, do I think that number is going to get bigger or smaller? Well, generally, if you take a number and you divide it by 10, it's going to get smaller, at least in this case when we're dealing with, integer value, or, well, not integers, but it's not like fractions divided by a fraction or some kind of weird thing. We're talking about you take something like 2.1, you divide it by 10 6 times, it's going to get smaller. So let's move that decimal in the direction that makes this smaller, which is to the left. So how do I know how many places to do that? Well, once we move it past the 2, there's 5 more places to move it. So that should give us 5 zeros. 1, 2, 3, 4, 5. 2, 1. Submit. Yeah, and it's good with that. Technically, they like it if you put the 0 in front. Most people like to put the 0 in front. I've never quite understood the point of it, but most math books consider it proper to write it as 0.0 rather than like 0.00, but notice how it gave me the right answer because it is mathematically correct. Okay, so that's how you go from scientific notation to standard form. Now, how did we go from standard number to scientific notation? So remember, we want a number in front, and then we need a value for an exponent. So the number in front has to be between 1 and 10. So where can I scan this decimal to end up with a number between 1 and 10? Oh, right here at 4.9. So the number in front is going to be 4.9. That's the only place you can put it where you get a number between 1 and 10. And then we ask ourselves, how many decimal places did I have to move that decimal in order to get 4.9? Well, it started here. I had to move it 1, 2, 3 places, so it's going to be 3. Now, before I hit enter, I'm going to ask myself, okay, is that exponent supposed to be positive like I have it written there, or should I put a negative in front? I have to figure out which one it's going to be. Is it -3 or +3 that I'm raising this to? Well, think about it. If I put 4.9 times 10 to the 3, would I get 0.0049? No, I would get, 4,900? We want to go the other direction, so it looks like I need that negative in front. So I submit the answer. There we go, getting them all right. Right, and this is kind of the argument that I'm making. They're using a little bit different wording, but they're trying to get you to understand the basics of, do I move left or right? They're saying 0.0049 is small, therefore we're going to have a negative exponent up here, which is essentially what I'm saying, right? When you multiply by 10, is your number getting bigger or smaller? If you can just keep track of that, you'll always know whether your exponent should be positive or negative, right? So I feel like probably people are pretty good at that by now. Now what we get into is, well, how do I do operations with those numbers? Like, that's great if scientific notation is a much more accurate and convenient way to write really, really big numbers and really, really small numbers. But what about when it comes time to do multiplications and divisions and additions and subtractions? The additions and subtractions are pretty straightforward. So I'm just going to kind of let you work on those because there's nothing, in my opinion, very tricky about those. But let's look at the multiply divide. So what is the quotient? Okay, quotient makes you think what? What word should you think of when you hear quotient? Division, right? You should immediately think about, oh, I'm dividing things. This is division. So I've got the division of 3.013 times 10 to the 8th and 6.55 times 10 to the 5th expressed in scientific notation. So notice how they're specifically telling you the number should be in scientific notation, because that's actually the one thing that we have to be careful about. Most people, as you'll see, the multiplication and division of scientific numbers, scientific notation numbers, is pretty straightforward. But what you have to look out for is that sometimes your answer is not in scientific notation anymore, right? Well, in a chemistry class, if you start off with your lab instructor's not going to care that, well, you started your lab write-up with scientific notation, but by the time you got done, nothing was in scientific notation anymore. They're not going to go, well, at least you started the right way. They're going to mark you down a bunch, right? And the reality is, it's not just because your teacher's going to mark you down. It's also because your work's going to get sloppier along the way because you're using numbers that are in a sloppier form. They're not in scientific notation anymore. So always at the end of the problem, you just do that check again where you go, okay, do I have to adjust this number for scientific notation? And if you're thinking about when the number gets bigger and when it gets smaller, it's a real easy adjustment to make. You just have to remember to do it. I think that's like when I'm grading papers, it's not that people do that step at the end and do it wrong. It's generally just that they forget to do it. Okay, so what am I talking about? I think with this one, we're going to get the case that I'm talking about. So let's do it here. So we want the quotient, so we're going to get was it 3.013? I'm sure that's wrong. Let's see. Oh, 3.013 times 10 to the 8th divided by times 10 to the fifth. 6.55 times 10 to the fifth. Okay, so here's our number, right? Here's the quotient that they gave us in the problem. Let me double check. So I've just put it in a mathematical form here, right? Excuse me. Okay, so let's, like, these numbers are going to be a little bit hard to simplify directly. Let's get, in this case, you're probably going to bring out a calculator, right? In this class, you want to try to do almost everything without using a calculator, but in a situation like this, no one's ever going to do this division, 3.013 divided by 6.55 by hand. Why would you? So I get 0.46. So when we do that, we're going to get, let's see, where's my equal sign? Equals 0.46 times 10. So basically your procedure here is you take the A values, those ones out in front, and you do the division there. And then you use your rules of exponents to simplify these powers, these exponent powers right here, right? So if I do that, how do I simplify 10 to the 8th over 10 to the 5th? Well, 10 to the 8th over 10 to the 5th, remember that's where we subtract exponents, so we would end up with 10 to the 3rd. If we have 8 x's on top, or sorry, 8 10s on top, 5 10s on bottom, we're left over with 3 on top when we simplify. So it looks like this. So our division that we just did is correct, but I'm not ready to put my answer in the problem. Why not? They've made it very clear they want our answer written in scientific notation, which you should always just kind of do. Whenever you're working on something, whatever notation your problem starts in, you want to finish in that same one unless you have a good reason to convert it. So, you know, you might be working on something where like it's point slope form, but you're like, I always think things should be in slope intercept form when I'm done. If you have a good reason for it, go ahead. Otherwise, the standard is that you put it in the same form you started with. So since we're starting with scientific notation, you should end in scientific notation. So this is not in scientific notation, is it? Why? Because this number out front that we refer to as the A number, that's not between 1 and 10, is it? So we have to make an adjustment to that. And here's where it's not bad. It's not hard to make that adjustment, but you have to remember to do it. You have to recognize, oh, wait, that number's not in scientific notation. So what do? We balance this number. So I'm going to move this decimal to get me a number 4.6. That's between 1 and 10, right? But what did I just do? If I just move the decimal and don't change anything else, I effectively just increased our number by a factor of 10, right? So we have to balance. So if I increase this part of the number by a factor of 10, then what must I do over here by a factor of 10? Decrease. So I increased by a factor of 10 over here. To balance that, I'm decreasing by a factor of 10. So it now becomes 10 squared. Does that make sense that these two numbers are equal? If you take 0.46 and move the decimal 3 times, that's the same as starting with 4.6 and moving the decimal 2 times, right? So that should be our answer. Let's see if I got this right. 4.6 times 10 squared. And got it. So you can see they did the same thing I did. They made a fraction. They simplified each piece separately. And then they basically stole a power of 10. Well, they stole a power of 10 from over here and placed it over here. I'm not in love with the way they're writing this problem out, but it's correct mathematically. It's just not how I would explain it. But basically, you take a power of 10 from over here, you put it over here to adjust things, and then it works, right? Your multiplication works the same way. Let's see if they give us a multiplication. Yep, here we go. The product of 2.5 times 10 squared and 3.7. I think that one's going to come out where we don't have to adjust it, but let's take a look just so you can see how this goes. So 2.5 times 10 squared. 2.5 times 10 squared. And And we want this to be a multiplication. I see it's throwing an error at me. Just a second. 3.7 times 10 to the 5th. 3.7 times 10 to the 5th. Oops, I do have a typo. Should be 2.5 times 10 squared and 3.7 times 10 to the 5th. See how it's always a good idea to check those problems when you write them down? Go back and double check. I would have just done that whole problem wrong and had to redo it. Okay, so when I'm going to multiply these out, so again, probably you could do this by hand, but probably use a computer. 2.6 times 3.7. That gives me 9.62. So yeah, that's what I thought. We're not going to have to adjust this one, but that's okay. 9.62 times 10 to what power? Well, if I have 2 10s over here multiplied by 5 10s over here, that's a total of 7 of them. So times 10 to the 7th. And we got our answer. Notice, oops. Oh, I hope I was showing it next. Yeah, I think it was on screen last time. Notice how 9.62 times 10 to the 7th is all. I didn't fix the typo. Which one? Let's see. 2.5 times 10 squared. 3.7 times 10 to the 5th. Which typo did I fix it? Oh, it's retracted. Okay, so we're good now. Okay. So 9.62 times 10 to the 7th. Notice how that is in scientific notation, right? This number out front, that's between 1 and 10, so that's good. 10 to the 7th, that's legit. So this scientific note, this is all ready to go. We didn't have to adjust it like we did the one up here. So was it 9.62? 9.62 times 10 to the what? 7th? Yeah, 10 to the 7th. Submit answer. Uh-oh, what did I do? Maybe I did. I do still have a typo somewhere. 9.62 times 10 to the 7th. 3.7 times 10 to the 5th. What? 9.62 times 10 to the 7th. Did I, anybody see, am I messing something up here? 10 to the 7th. Oh, I see. In my calculation, I had done the first part first, so I have to do 2.5 times 3.7. Maybe that's what they were you were telling me in the chat there. I get it. So this should be 9.25. There's my mistake. 9.25. Somehow I hit the wrong button when on the calculator, which is actually a good lesson as well. A lot of people think anything that calculator is showing has to be true. But I'll tell you, there's lots of times where you hit the wrong button on the calculator and don't realize it, and then you trust this number that came out, and it's wrong. So this should be 9.25. There we go. There we go. So just user error on the calculator is what that was, right? I used it wrong. Okay, so that's what that'll look like. Let's see if they have one where I'd like to see a product. I'll just get one wrong. I want to see a product that we have to do an adjustment. I don't suppose it'll give us one on the next try. Here we go. This will do it. This is what I was looking for. So here's a product, and we are going to have to adjust our number when we're done. So 3.4 times 10 cubed. 3.4 times 10 cubed. 3.4 times 10 cubed, and 8.8 times 10 to the 6th. .4 times 10 cubed, 8.8 times 10 to the 6th. Okay, so we want to multiply these numbers together. So what do? We multiply the a values in front. So I'll use my calculator here. I guess I should show the calculator. It's just your basic Windows calculator. 3.4 times 8.8 equals 29.92. 29.92. Let's double check I did that right. Okay. And then times 10 to, well, 6 and 3, that we add those, so that's going to be to the 9th. So this is our number, but this red flag should go up and go, wait a minute, that initial number is not between 1 and 10. We have to adjust that. So what do I have to do? I'm going to move the decimal to the left, which means I'm making this number smaller by a factor of 10. So to compensate, I have to make this part bigger by a factor of 10. So this will become, I'm not going to have room. Let me do it on the next line. This is going to become 2.992 times 10 to the 10. Right? This part got smaller by a factor of 10, so this one has to get bigger by a factor of 10 to compensate it. So let's see, 2.992 times 10 to the 10th. All right, got it right. So same idea. You just multiply the a's together and then use your rule of exponents to simplify that part. Simplify it all down and we're good to go. Okay? Once you do 3, 4 of those, you probably have the hang of it. Okay? So let's go back and look. So I think, let's see, remind myself what these look like. Yeah, so these are pretty straightforward, basically. So Brianna broke a cell sample into 12 batches, each weighing 8.7 times 10 to the negative 5th grams. So see how, and that would be small. That would be what, 0.000087. That's pretty small. It's a little easier to write it in scientific notation. So really, really small numbers, really, really big numbers, convenient to do this way. You just take this number and divide it by 12. No. Multiply by 12, right? If each sample weighs this, how much did the original sample weigh? It would be this times 12. So that's all you'd go through and do. So not a big deal. And you could put 12 in scientific notation form, right? 12 is 1.2 times 10 to the 1, right? So any number you can put in scientific notation form that you want. Okay. Wait, didn't we do that already? Why is that not due yet? Yeah, we kind of talked about exponents. Okay, I must just have a weird date on that homework assignment. Okay, so polynomials. So we're kind of getting into the introduction of polynomials here. So there's some terminology, and then there's adding and subtracting polynomials. I don't think we've talked about any of this yet. Yeah, that was my other class. Okay, so what is a polynomial? Polynomials are just a new type of object that you're going to deal with in your math classes a lot. Okay, they come up a lot. So, well, I should say it depends what you're taking. You're going to deal with polynomials a lot in intermediate algebra. So your math 3 class, when you take that, you're going to deal with them a lot. You're going to deal with them in, if you're calculus based, so trigonometry has some polynomial related stuff into it. You don't usually deal directly with polynomials, but a lot of the things you learn about how to deal with polynomials carry over into trigonometry. Pre-calc, college algebra, ultimately calculus, those classes are just chock full of polynomials. You'll deal with them all the time. So what is a polynomial? Well, a polynomial is something that looks basically like the following. So here's an example, 3x squared. Actually, let's make it a little more complicated. To the 4th plus 2x squared minus 3x plus 7. So this is an example of a polynomial. So let's talk about it. What's going on? What makes this a polynomial? And what if we changed it would make it not be a polynomial? How would that work? Okay, well, notice how we have a set of terms here, and those terms all follow a basic pattern, right? We have four, we call, in a polynomial, we call it each of these that are separated by a plus or minus, we call that a term. So this would be considered a 4-term polynomial. And we'll have names for the certain term, the number of terms in a polynomial, but we'll get to that in a little bit. So right here we have 4 terms. Notice how they're written in order of decreasing exponent. You always want to do that unless you specifically have a reason not to. But your default should be to put them in this organized form. It just makes things so much easier for your work. If you don't do that, things get so disorganized that it's so easy to make mistakes. So this is what we call standard form, where the biggest exponents are in front, smallest exponents are in back, right? Notice how, like, some people get worried where there's like, well, wait, there's no x cubed term. Well, if it makes you, we don't need it basically, but if it makes you feel better, you could consider it plus 0x cubed if you want it, if it comforts you so that it doesn't worry you that there's a term missing in there. You could just write it as that. But we do that every once in a while for specific reasons, but we usually don't write it this way. You would just recognize that that's the same as the original polynomial that we had, and then you would just, it's much more convenient to just write it this way. So don't worry if there's an exponent missing. Some students get all like nervous about that. It's not a problem. Each term in the polynomial follows a pattern. There is a coefficient. That's the number that multiplies the variable, and there is an exponent on the variable, and there is a variable. Okay, so there's a coefficient piece, there's a variable piece, there's an exponent piece. You have those 3 pieces in there. And you might say, wait a minute, I think these 2 terms out here on the end, I think those contradict what you're saying. And I'll say, hold on, they don't, but we'll get to that in just a second. So here on the first term, we have 3x to the 4th. 3 is the coefficient, x is the variable, 4 is the exponent. Right here, 3 is the coefficient, x is the variable, 2 is the exponent. Right? Over here, now here's where you go, here's where we're going to catch it, Dr. Frederick. You said they all have an exponent. There's no exponent here. Of course there is. Negative 3x is the same as negative 3x to the 1. We just don't write the 1, but we know it's there, right? We use that when we do our rules of exponents. If I do x to the 6th times x, I know that gives me x to the 7th because it's 6 plus 1, right? So this still, 3 is your coefficient, x is your variable. Sorry, did I just say that wrong? 3 is your coefficient, x is your variable, 1 is your exponent. We just don't write it that way, okay? We write it like that. All right? And you go, okay, but we got you on this one because this one doesn't even have a variable. So there's no way you can say there's a coefficient, a variable, and an exponent here. And I will say, yes, there is. Because remember, anything raised to the 0 power is 1. So 7x to the 0 is really the same as 7, right? So yes, and it might seem like, well, you're just making this up. This is just rhetoric so you can say you're right. No, we actually consider this a 0-degree term, which I'll explain in a moment. So 7x to the 0 simplifies to 7, and yet it still has a coefficient, a variable, and an exponent, right? So I just used a term a minute ago, this term degree. What does that mean? The degree of any term in a polynomial is the exponent on that variable, right? It's for one right. In this class, we're only dealing with one variable per polynomial. Actually, we might deal with 2. The degree is the sum of the exponents in that term. But in this case, we only have one variable each, so we don't really have to worry about that. So you loosely can think of it as the exponent that occurs in that term. So this term right here, that's a 4th degree term. This is a 2nd degree term. Remember how this is 3x to the 1? That's a 1 degree term. And this one, you guessed it, 0 degree term. Okay, so it's not just semantics where I'm trying to argue that they all have coefficient, variable, and exponent. They actually do, and the language depends on us understanding that. Okay? Now, so we have the degree of each term, which is the degree of the exponent in that term. Then we have the degree for the whole polynomial. So what would the degree of the whole polynomial be? It is the degree of the highest term in that polynomial. So this polynomial written here, we would say that's a degree 4 polynomial because the highest degree in it is a degree 4 term. And we go, why is that important? What you'll see in college algebra or pre-calc, if you take one of those, is that this term right here has the most control over this polynomial as far as the graph and all sorts of behavior. This one kind of calls the shots. So the highest degree term in that polynomial decides a lot of the characteristics of that polynomial. So some of you will go on to learn, oh, a degree 4 polynomial has these kinds of characteristics. A degree 5 has these kinds of characteristics. Degree 6 has this kind of characteristics, and you go from there, right? So this is a 4th degree polynomial. Let's see. Let's do it this way. Okay, a polynomial that just has one term in it is called a monomial. Monomial. That's a one-term polynomial. A polynomial that has two terms, you might be able to guess, a binomial. So if there's two terms in your polynomial, it is a binomial. Bi meaning two, bi polynomial, two-term polynomial, binomial. The ones that you ultimately will end up dealing with the most, trinomials. Guess how many terms are in a trinomial? That's right, 3. Okay. Beyond that, we don't really give them names because you're not going to see them as much. By far, the most terms you're going to see are monomials, binomials, trinomials, and even then, most of them will be trinomials once we get out of this first chapter. When you start using factoring for the rest of this course and your Math 3 course, your intermediate algebra course, and then your other courses, you'll start seeing trinomials like 90% of the time. But right now when we're learning, you're kind of getting the hang of all of them, right? So a little bit differently there. So that's a trinomial, and that shouldn't say 7. Now, I thought I said 5th before, but I hit the wrong button. These shouldn't be the same. If they're the same, we can add them up and combine them, right? Which we'll learn about in a little bit. So this would be a trinomial. This is 3 terms that cannot be simplified any further. That's a trinomial. Okay, so you've got the degree you have to consider. You have to think about how many terms are in the polynomial and what kind of things we do with it. Okay. Let me double check here. Right. So then we get into adding polynomials. Once we kind of and your exponents on your polynomials, they cannot be negative, they cannot be fractions, they cannot be they can be 0, but they can't be negative, they can't be fractions, so it has to be things like this. Like people get the hang of what a polynomial looks like pretty quickly generally. So what if I wanted to add or subtract polynomials? So let's think about that. To add/subtract polynomials, combine like terms. So in fact, let's put that on a different line. So to add or subtract polynomials, just combine like terms. Okay. What does that mean? What do you mean combine like terms? What are you talking about? Like terms are ones that have the exact same variable associated to them. So up here we have no like terms because these, like here, this is x to the 7th, this is x to the 5th, this is x. And sometimes a student protests and say, yeah, but they all have the variable x. Right, but a 7th degree x is different than a 5th degree x is different than a 1st degree x, right? Think about it in terms of measurements. A 1st degree measurement would be the length of the wall. So just look at a wall in a room that you're in and think about measuring the length of that wall. That's a 1st degree measurement. A 2nd degree measurement would be something like area. That's how much carpet you have or flooring you have in the room. If you're going to replace the flooring, what is the area of the floor? So you know how much carpet or wood or synthetic or whatever you're getting. Does it ever make sense to add the length of a wall to the area of the carpet in the room? I cannot think of an instance where that would possibly make any sense, right? So even though they're both measurements and they're both in feet, right? Linear feet versus square feet, they're different dimensions, which means it doesn't make sense to add them together. Same thing here. Sure, these are all based on the variable x, but they are different dimensions of x. So it doesn't make sense to add those things together. So like terms are the ones that have the same exact variable type. So, you can think of it this way. We're really just counting how many of each type of thing that we have, right? So if you go out and, let's say you deal in vegetables and fruit and stuff like that, right? So you've got 5 apples and 3 oranges. Can you combine those together? Not really. As I have 5 apples and 3 oranges. That's the whole story. There's nothing simpler to get, right? But what if I had 5 apples and 3 apples? Well, then it would be easier for me to say I have 8 apples, right? So think of it that way. We've got 5 apples plus 3 apples equals 8 apples, right? That's kind of our model for how we're going to do this. So it stands to reason that if I have 5x squareds, right, whatever that means for the problem we're working on, but I have 5x squareds, and then I gain another 3x squareds. How many x squareds do I have? I have a total of 8x squareds. When we are adding or subtracting, all we're doing is counting. That's all we're doing, right? So just like we have 5 apples plus 3 apples is 8 apples, 5x squared plus 3x squared equals 8x squared. Notice how when we were adding the apples together, our unit didn't change. It was apples at the start. That looks weird. Is that spelled right? Apples. Is that how you spell apples? Yeah, that's right. I don't know why that looks so weird for some reason. I think it's kind of a weird font. You start with apples, you end with apples. The apples didn't change. If I have 5 apples and you give me 3 more apples, they don't become apple squareds. Right? What's an apple squared? But that's what people do. They change this. They'll change here. Like here's a common thing that I'll see. People go, oh, well, 5x squareds plus 3x squareds, shouldn't that be 8x to the 4th? No, because we're adding things. And when we add, that doesn't change our unit, right? The x squareds is like our unit that we're counting. Just like apples up here didn't become apple squareds. This should not become x to the 4th. This just becomes x squared. So you should not end up, when you add polynomials, you should not end up with new exponents that you didn't have originally in the problem. Occasionally you'll lose one if things cancel out perfectly, but that very rarely happens. But you shouldn't get new ones. You shouldn't all of a sudden have an x to the 5th if there was no x to the 5th in your original problem, right? It's just like this. 5x squared plus 3x squared is 8x squared. So, just like our example with when we had, 5 apples and 3 oranges, if you have 5 x's and 3 y's, you don't have 8 of anything, right? Well, I've got these 5 x's over here and I've got these 3 y's over here, but they don't really affect each other because they're different types of things. So if the variable is different, we cannot combine those. If it's the same variable but to a different power, we cannot add or subtract those together. So it's very simple. You're looking for things where the variable type is exactly the same, and then you combine those. So let's take a look. 9 minutes. Okay. Yeah, we got time to do a few of these. Okay, so let's say I'm looking at 3x squared minus 4x plus 7, and I want to add to that 2x to the 4th minus 7x plus 6. And I think usually, I don't know, we won't have time to do a ton of examples, but once you get the hang of addition, you just have to remember for subtraction, you're just subtracting instead of adding, right? There's no like special fanciness to do subtraction. So I want to add these 2 polynomials together. All right, well, I'm just going to look for things that are like terms that I can combine. So let's see. It's a good idea to start with the highest degree term. All right, highest degree term. Oh, 2x to the fourth. Is there something I can combine the 2x to the fourth with? No. Okay, well then it just stays 2x to the fourth. Right, there's no change in that value because there's nothing to combine it with. Okay, the next one, 3x squared. Oh, nothing to combine that with. Okay, so that becomes plus 3x squared. Okay. Okay, what's next? Negative 4x minus 7x. Okay, so if I'm in a debt of 4 apples and then I end up borrowing another 7 apples, how many apples do I owe? I owe 11 apples. Right? I'm getting myself in an apple debt. So minus 11x. So negative 4x minus 7x. They were negative 4x and negative 7x have the same variable type. That is x to the 1. So we can combine those through addition. Whoops. Hit the button too many times there. And then 7 plus 6, you've known how to do this for a long time. That's just going to be plus 13. Plus 13. And notice how my answer is, as soon as it compiles here, is written in that standard form that I talked about. Biggest exponents first, smallest exponents last. So it just works down in that organized order of decreasing exponent. That's how we write the problem. So that's all there is to addition. You're looking for things that have the same variable type. You're combining them, and you move on. Let's do another one. So 5x cubed minus 3x squared minus 5. Let's make it, yeah, minus 5x plus 2. And then 6x squared minus 3x plus, I don't know, 9. Oops. And we're not doing multiplication today. That's probably next time. Let's make this a plus. Okay, so I've got, let's wait for it to compile so I don't confuse anyone. There, we've got the plus in there. I want to add these together. Okay, well, I'm looking for a cube term. I just see the 1. So that informs me that there's nothing to combine it with. 5x cubed. Okay. Now I've got some squared terms. I have a negative 3x squared and a plus 6x squared. So if I owe 3x squareds and then I come into 6 of them, I now have a surplus of 3x squareds, right? So plus 3x squareds. Notice when I'm combining these, the variable type is not changing. It's staying the same as the original types. This gets confusing because later when we multiply terms like this together, the exponents will change. So just kind of get it straight in your head. When we add or subtract, the exponents don't change. When we multiply, they generally do. Okay. All right, negative 5x and negative 3x, those are like terms. So that's going to give me negative 8x. And then 2 plus 9 is plus 11. So here we have our, as soon as it renders, there we go, polynomial written in standard form. That is the sum of those things. If we were doing a difference problem, a subtraction, all we would do is be subtracting like terms instead of adding them. So it's not like a complicated procedure at that point. Okay? So that's the adding and subtracting of polynomials. Don't have time to get into the new topic of multiplying. That's a pretty big topic. It's not hard. Most of you will pick it up very quickly, but it does take some explaining. So I can't really do that in 3 minutes. But we will start with polynomial multiplication next time. We will go over that and go from there. So please keep yourself caught up. If there's any kind of concerns or anything like that, do please contact me, either office hours, email, whatever you need to do. Get a hold of me so I can help you with whatever the concern is that you have, and then get you moving along comfortably towards success again. Okay. Thanks, everybody. So with that, I'll close down the YouTube stream. I'll give a couple minutes in case anyone wants to talk to me after class. Otherwise, I'll see you in a couple days. All right. Thanks, everybody.